start out by doing that. We're going to go down here, and I want you to hit open. Okay. Now, what I always recommend over here in the file directories, just go all the way to the top where it says this PC and minimize that. That'll help collapse everything. And then when you hit the plus arrow or the plus again, now you can go to your thaw space, go to your folder for this class, okay? And in your folder you should have that file that we created the other day, the WinMax notes file. And go and hit load. Okay. Everybody's load okay? Good? Something wrong? We can click on it or double click on it, and it should take you to this page with your notes. All right. Now I do want to show you something real quick, because I'm not completely blind, but I also don't like having to squint to look at stuff, and I know that by default the text is really small on the WinMax. If you want your font to be a little bigger like mine, very simple. You go to editor settings right here, and then you click on editor font, and it should bring up a select font thing where essentially you can make it as big as you want it to be. I've got mine up to 20. Okay, and then it just makes it easier to read. Okay, everybody do your own there. If you like it small, that's fine. If I come over and you ask me for help, I'm probably going to make it bigger so I can read it easier. Okay, but real simple thing. You can make the font bigger so it's just easier for you to see. All right. Now, remember the other day I showed you that when we saved that, it saved two files in our folder, right? One file was the NC file. The other file, we have it set in WinMax. We have it set to automatically save the NC state. All right. So we are going to go to the input screen here. All right. We're going to go to import export functions. And we're going to hit import NC state from file. Now in your folder, it should automatically go to your folder because that's where we just opened the file from. There should be that NCSX, NC state, don't ask me what the X is, okay, file that you can click on. You guys all right?
Yeah, what's the first step?
We hit import, we hit begin operation. The NC state was imported successfully. Did everybody get that notification? Hit OK. It should jump back to the screen. When we save this file, after we create our tool library today, we're going to save the NC state. Okay, so that file, the tool library is going to save with the NC state. We're also going to export the tool library to make it a standalone file in our thaw space. We've got it two places. That way if we lose one or the other, we're good. And every file that you do for all the lessons and everything, when you hit save on them, it's going to save all the tools that you're using that are in your tool library with it. So when you open that file back up, you can just import the NC state and it'll automatically bring in all the tools. But we're going to make sure we have that backup tool library as well. Okay? All right. So let's go ahead and get started. Let's go to the tool library button. It's right here, tool setup. So you can go here. There's about 6 different ways you can go over here. You can hit the manual tab and go to tool management and go to tool setup. But I typically, when I want to get there, I usually do the hotkey. I hit Control T. Even out there. When I want to get to my tool setup, I just hit Control T on the keyboard. Okay, the machines out there all have keyboards that slide out, and I usually have it out when I'm working on the machine. Because no matter where I'm at in the control, if I hit Control T, go to my tool setup. Okay, or you can just click the little tool holder right here. Okay, my tools, I thought I cleared them out, but I had tools in this program when I saved it the other day because I had tools on my thing. So give me a second. Let me clear my tools. You shouldn't have anything, right? You're just like sitting there at tool 1 with nothing there, all zeros. Good. Let me clear my tools real quick. There we go. That what yours looks like? I just did that, but then when I loaded that NC state, because I saved that file the other day with those tools still in my control, it saved them with that file. All right, so let's work on tool number 1 here. Okay, tool number 1 is an 1/8 inch flat end mill. Okay, it's the second page of mill lesson 2 in your workbooks. So here's how we do this. Anywhere you plug in data on WinMax, if you want to keep that data there, you have to hit the enter key to store it. I know that sounds pretty basic, but what people like to do is just hit the arrow key, and if I type something in, like here, if I tell this is an end mill, or if I type in a diameter 0.125 and I hit the arrow key, it goes back to zeros. Okay, so for tool 1, we got tool 1, I'll type 1 enter. I'll tell it what type of tool it is. So I can pick that out of the list here. I'm going to tell it it's an end mill. Okay, this is just a standard flat end mill. For the diameter, I'm going to type 0.125 for an 1/8 inch. But I do want to show you this because I think this is nice to know. Okay. On WinMax and Mastercam, okay, these CAM softwares, anywhere that you can input numeric data, it will do math just like a calculator for you. So let's say I get a 5/32 end mill. Who knows what 5/32 decimal equivalent is? I don't either. All right, I could sit here and figure it out if I did, up and down math. Or I can just type 5 divided, which is the / by 32, and I hit enter, and it does it for me. Okay, so on your number pad over there, on the right of your keyboard, the / is your divide, the asterisk is times, the minus is minus, and the plus is plus. I could type 5 plus 5, enter, I get 10. I could type 10 minus 2, enter, I get 8. I could type 20 times 25, or not 225, 25, and I get 500. It doesn't like that. I get this warning. It says, hey, we've got a maximum of 100 or 99.999 inches for an end mill. So we aren't programming any 125 inch diameter end mills in WinMax. Think about that for a second. We're talking 125 inches is basically how big around? It's 10 feet, right? We can't program any 10-foot end mills. I'm okay with that. All right, so what I plug in here needs to just be what I'm using. So I have 1/8, enter. Okay. For the lengths, we are going to just plug in an arbitrary number in the classroom. Okay. That number, we're just going to plug in 5. Okay, we're just going to set everything at a 5-inch length. Out there at the machines, you need to know this, out at the machines, we'll set those lengths because every tool is just a little bit different in length. Okay, our drills sometimes are in drill chucks. They're like 8 inches. Our end mills in a little short ER collet holder might be only like 3 inches projection length is what it's talking about. How much of that tool is sticking out of the spindle? And that's what this value is. So if this is my spindle nose, I got my tool here. And I got my cutting tool right here. It's saying how much of this tool is sticking out of the spindle. Okay? That's what it wants to know. Absolute tool length is what we use on all of our controls. There's 2 ways to set tools off on a mill. Negative position, absolute tool length. Okay? So if you've worked on a mill before and you're like, well, when I set the tool lengths, they're all a negative distance. Well, they're a negative distance from where the spindle is at home down to where you set the tool off. And you store that negative value. And then in your offset, you're going to tell it how far is it from where you set the tools up to the top of your part, or wherever your Z0 is set at. Our machines are set up with what we call a tool calibration length. I can show you that. Okay, right here, this Z reference, that is stored in our machines. we use common gauges to set. So it knows exactly how far it is from when the spindle's sitting at home, or what I call tool change height. It knows how far it is from there to the table. And that is what that Z reference number is that gets calibrated at the control. Then we could set up gauges. So let's say I'm using my 2-inch 1, 2, 3 block. So let's say it's negative 20 inches down to the table, and then I'm using a 2-inch 1, 2, 3 block. It says my calibration length it's going to use is negative 18. It takes those, it combines them, and then when I store the tool off the top of that 1, 2, 3 block, it gives me how much of that tool's sticking out of the spindle. It does the math for me. Why do I like this better than negative tool lengths? Anybody have an idea? It's automatic. I don't have to do the extra math for up to the Z height. But what I like more than anything about this and using absolute tool length is, when I'm out there at the machine, I can pull my tape measure out or my pocket scale, and when I set a tool, I can take my pocket scale and I can hold it up and kind of look across the tip of the tool, and I can visually see if it's stored correctly or where it should be. Most of the time, if a tool doesn't store right, something's off in your calibration. Usually it's going to be an inch or two, because you're either using the wrong side of the block of the tool setter, or maybe somebody went in there and messed with the reference gauges. Okay, so I can visually look at that. When we get out the machine, I show everybody how to do that. All right. I say that older controls don't have absolute values. Okay, older controls don't. So you'll have to learn how to set them at the negative length. The 2006 model Daewoo's with the Fanucs that I run a lot for the guy up north, those, as everything's negative. You have to bring the tool down and give the negative value, and then you got to give it a positive Z back. If I set everything off the table and my part's up here, I got to tell it how far it is from the table back up to the top of my part, and I set that as my Z offset. It's a positive distance from where I stored all my tools. Okay? All right. Now, speeds and feeds for these. Let's look at our chart here. Let me get to where I can bounce back and forth. Okay. Not that chart. This chart. This chart. We're going to calculate the RPM. RPM is cut speed times 3.82 divided by the diameter. I want to show you something here. Your machinist calculator, I had you get them out, and then now I'm sitting here going, well, I probably didn't have to do that, because WinMax is going to do the math for us. But I'm going to have you double check it on your calculator. Okay, I want you to double check it. If you didn't score what you would like to have scored on that quiz the other day, you get to retake it on Monday. Okay, you get to take it again. Same quiz. Go study it. Make sure you can punch stuff in on your calculator and get the right answers. Okay, I'm going to show you at the end of class how to go look at it, so you can literally look at the quiz, practice it to where you're doing good. If you feel good, you got a 27, 28, 29, something like that out of 28. All right, you're going to get out of here a little bit earlier on Monday. Okay, but everybody's going to take it again or get the opportunity. Okay, so let's look at this tool. Cut speed, we're going to set all our tools up for aluminum in here. So right here is our cut speed, our SFM, 1000. So over in WinMax, for the speed, what it's asking for here is the RPM, right? It wants the RPM here. Surface speed, surface feet per minute, that's where I would plug in my 1000. Bum, bum, bum. Now it just did the math in the background, but what did yours plug into the speed there? Did it plug 12,000 into? Good. So we're all on the same machine. This is all this is set up to the VM machines that we have out here, which have a max spindle speed of 8K. The 12,000, or sorry, I said that backwards. These are all set up to a VM10U, which has a 12K spindle. But our machines out there, if you look underneath there, you see where it says VU max RPM 7750. Okay, that's our max RPM on all these smaller mills right here. So anytime that a tool calculates to an RPM higher than that I'm literally going to be programming with, I've got to just plug in the RPM. 7750. The next thing that people tend to look at when they do that, all right, I plugged that in. Now see how surface speed has CAL after it? It just recalculated it. Because when I override the RPM, it's got to be able to do the math both ways. So now, since we can only run our RPM at 7750, our surface feet per minute's actually only 254, which is about a quarter of what this tool is capable of. Why does that matter? We can always slow stuff down and it's going to be okay. But why does that matter in the grand scheme of things? You're running your RPM lower, which is going to reduce your feed rate, right? Because everything's based off the RPM. So your metal removal rate's going to be slower. So when you're in industry and you got an employer that says, well, that 8,000 RPM spindle's $5,000 cheaper than the 15K. Make sure you remind them, hey, we cut a lot of materials that we've got to back all this other machine we're running. We got to back off all of our tooling because the machine doesn't have the spindle speed to run the tooling at the RPM it's recommended. If we could run that RPM, we could speed up our feed rates. We get more work done. You see the value? Everybody, there's reasons that there's entry-level RPM spindles and there's high-speed machines. And it's all about what you're doing. If you're cutting a lot of hard, aggressive metals, you need a high horsepower, probably not a lot of RPM spindle. Okay? If you're cutting a lot of mold and die stuff where you're doing a lot of high-speed machining and finish work, you need a high RPM spindle so you can move across that part and get stuff done. Checks and balances, right? We got to know where it applies. So we're going to be limited to 7750 in here. That number is going to get stored in your mind because you're going to hear me say it a lot. Until we get up to like a half inch, all of our tools are pretty much 7750 when it comes to cutting aluminum. Okay, so we're going to tell it on the coolant. We're going to tell it primary. We are going to run coolant in these programs that we program, and then it wants a feed per flute. Okay, so chip load, parenthesis, IPT/FPT, feed per tooth, feed per flute, same thing. So for an 1/8 inch, it wants 4/10 per flute. So right here I'm going to type in 0.0004 and I hit enter. Okay. Over at the right hand side of your chart, over here you see flute selection. For non-ferrous soft metals, we're setting up for aluminum. Anything 1/4 inch or over, I prefer to use 3 flute end mills. Anything under a 1/4 inch, 2 flute. And that's all based on chip evacuation. When you get into smaller cutting tools, obviously the flute size is smaller as well, right? Well, they make 3 flute 1/8 inch end mills, but what you have to be careful of during the application, if you try to slot mill with them, there ain't hardly any room for chip evacuation, and it'll load up the chips in what we call galled. Okay, it'll galled up and weld itself to the tool, and then it'll break the end mill. So 2 flute end mill, we're limited on how fast we can feed it, but there's less of a chance of us breaking it. When you get up to 1/4 inch and above, you got a big enough tool that the chips can get out of there. Okay, that's a subjective thing to me. Now there are times where if I'm setting up a production run on something and I'm using an 1/8 inch end mill and it's just coming in and cleaning out a corner, just a little profile milling, so that 3/4 of the tool's out of the cut and plenty of room for that chip to get out of the way, yeah, I'm going to go to a 3 flute end mill because there's enough for the chip evacuation, plus it adds one more cutting edge that goes into my feed rate. That's what, if you plug in 3 there, watch the feed rate, it automatically recalculate to 9. So now I'm 3 inches more per minute. If I could run this tool at its full RPM, watch this. 30,000 RPM. So I need a 40K HSK machine, you know, most of those high-speed machines are like 40,000, 50,000 RPM. But if I could run this tool at 30,000 RPMs with 3 flutes times my 4/10, I can feed it 36 inches a minute. That's 4 times faster, right? Makes sense? And these are the things that I just want you to wrap your brains around as we go through this, where high RPM spindles come in. If you're cutting aggressive, you know, stainless and a lot of tool stills and stuff like that, the cut speeds are so low that the RPMs are going to be low anyhow. You're not really gaining anything. All right, so we want 2 here. The feed rate, we are going to type in 6 there. I'm always going to put the whole number. We're going to round it down to 6. The feed per flute just recalculated based on the fact that I overrode the feed rate and put in the whole number there. RPMs and feed rates, drop the decimal. Just put whatever the whole number is. Don't round up. Just always drop the decimal and it's the whole number. Okay, we leave it at the whole number. Okay, that's tool 1. Let's go to tool 2. So just go to the tool number, type in 2. Tool 2 is going to be a end mill as well. Okay. Tool 2 is a 1/4 inch. Calibration length, remember I just said we're just going to plug in 5. We're going to make it, I don't want it to start with the spindle nose in the part when we do our draw screen. That's why I'm doing this. So we're basically, we're lying to it and giving it some arbitrary numbers like what it would be used to out there. There's a method, there's a reason I'm not just leaving it 0. So here, if I type in the cut speed and it does the math for the RPM, we're maxed out again. So we're going to do our 7750 RPM. We have been able to, we've increased, it's twice the size of the other end mill, so we've increased the surface footage by double, so now we're up to 507, but we're still only half of what this tool is capable of because we're limited by our spindle speed. Okay. The feed per flute for the 1/4 inch, what is it? 1.5 thou for the aluminums. Everybody see that on the chart? Right here. 1.5 thou, that's the aluminum chart. We're going to plug in 1.5 thou. And then for this tool, we're going to hit 3 because it's a 1/4 inch. 3 flutes. Feed. And drop the decimal and just type in 34. There's our info for tool 2. Does everybody's look good? Okay. What's the benefit of me taking the time to do this instead of just calculating these while I program? It's going to save time because what I'm going to be able to do is anytime I'm programming, especially in this workbook that uses just these 10 tools, I can go reference this as my point of view of what I need to do as far as tool calculations, okay? So let's take our calculator out. Let me open mine up here. And I'm just going to double check these numbers, plus I want to make sure that everybody's good to go on using this calculator. I'm going to double check these numbers. So on our calculator, I'll type in the tool diameter, 0.25. I'll hit diameter. I'll type in the RPM, 7750. And I'll hit RPM because we've got to override it. You know, we've got to tell it what we're actually able to do here. The calculator would calculate it for the full tilt. But if you hit SFM right now, you notice it automatically pulled in a cut speed of 507 because I overrode the RPM, so it recalculates the cut speed. Now, for the inch per tooth. Okay, actually, do this. Type in 34 and hit IPM for the inch per minute. Type 3, hit convert, and then hit number of teeth right here, which is the IPM button again. And now if you hit IPT, well, mine's rounding to 3 decimals. Hold on a second. Mine keeps going back to that. Okay, if you hit IPT, it's going to round it to 4, but you can tell it's giving us basically the same thing we've got there. It's just rounding it to 4 decimal places. Could I just type in the numbers of what's on the screen and let it calculate? Yeah, I could. But I'm just double checking the math, okay? I'm just showing you that it's doing the same formulas that are on this sheet. WinMax is doing the same formula. The calculator is doing the same formula. You've just got to plug your numbers in the right spot. I don't remember if there's anybody in this class, but I did have like 2 or 3 people in the other class plugged in on the triangles on that thing. They plugged in the side opposite as the side adjacent, and then it gave them the wrong side opposite number, but it was asking for the side adjacent. Pay attention to where you're plugging your numbers in. Okay. All right. Everybody got tool 2 okay? All right, let's go to tool 3. What size tool 3? I know it's an end mill, but somebody give me the size. 3/8, 0.375. Tell that's 5 inches long. I'm just going to plug in 7750 for the RPM. I know that until we get to the 1/2 inch tool, they're all going to be 7750. Based on that cut speed and what our tools are capable of doing. I wish I could go pull out the calculations. 15 years ago when I went through this program, okay, 15 years ago, our cut speeds for the tooling we had then was 600. Okay, the equivalent of today's tooling. Tooling has came along to where they're able to, basically they're still carbide end mills. They've changed some geometry, they've changed some coatings to where now you can run them at 1,000 and some much higher. There's some actual really high performance stuff that come in that they've got cut speeds up in the 2,000 and 3,000s that you can use. As a matter of fact, our tooling actually has a variable based on how you're using the tool. We program everything based on slot milling, and then we just run it at that. But it also has profile milling, which is a higher cut speed, and then it's got high feed milling, which is, or high speed milling. Sorry, I don't want to get the statement wrong there. High speed milling, which means a really light step over, but the full flute. But you can feed it super fast. Okay, you're just basically running it around there, and it calculates out to about 300 inches a minute for a 1/2 inch end mills, compared to like 90 is what we're going to get here in a second. So let's go ahead and plug in our feed per flute. Let's see here. I'm gonna call everybody out here. Kellen, what's my feed per flute for this tool? 3,000s. I like it. We're gonna have 3 flutes because it's bigger than a 1/4 inch. So we're gonna feed it at 69 inches a minute. Okay. All right. I would like you to take the next, I'll give you 10 minutes here. I would like you to do tools 4 and 5. Okay, tools 4 and 5. Use the chip loads. They're going to be 3 flutes. The RPM is going to be whatever it comes out to be when you plug in the cut speed. Okay, it will be a different RPM than 7750. So go ahead and take 10 minutes and give that a shot. let's take a look at those. I'm going to work through them. I've got to set them up just the same. So tool 4, that's my 1/2 inch end mill. Okay. 1000 cut speed. The RPM 7639. We're able to run our full, finally we can run our full surface footage. My feed per flute for my 1/2 inch is 4 thou. And it's got 3 flutes. So I'm going to feed it at 91 inches a minute. That look good compared to everybody else's tool 4?
We just type in 4 out on the tool number, pull it up.
Yeah, if you go back to, like, if you want to go back and look at another tool, all you got to do is go back here. Like if I want to go back to tool 1, I type 1, there's tool 1. I'm going to go to tool 5 now. Okay. Tool 5 was 3/4, right? I'm going to tell it that it's got a 1000 cut speed, 5093 RPM. And it's literally all it's doing is what we're doing. It's telling it, I'm going to clear this out. I'm telling it 1000 cut speed. I'm telling it that it's a 0.75 diameter. And it's calculating the RPM that way. It's the same formula when we do our tool library in Mastercam. The same thing's going to happen there. It's calculating it for us. These aren't VU formulas. These are industry standard formulas that the system uses, software uses, the calculator uses, the CAM system uses. Okay, it's the same formulas. Feed per flute for that 3/4 is 6.5 thou. It's got 3 flutes, so we feed it at 99 inches a minute. Okay. All right, has everybody got all 5 tools good? Okay. In the spirit of the fact that, a little bit of a winter storm, I think it's settled down now. But when I've done a little bit of work, and we've done 40 minutes worth of work so far, I want to save as I go. And right now we haven't saved this much work yet. If this computer crashes, it's gone. So let's first off go to our program manager and just hit save here. Okay. That when you hit save there, it saved it into that NC state with this file. You guys all right?
Yeah, my feed flute for number 5 was slightly different.
Okay. What was it?
It's 0.006479 instead of 6.
Is the feed rate 99?
Yeah.
Is RPM 5093?
Yeah.
You're good. It rounded this a little different, is that what you're saying?
Yeah.
Your diameter is good, right? 0.75? Let me look at it. We're going to go back to the input screen. I want you to go to import export functions, and I want you to listen right here. Don't click or do anything until I tell you to. Don't try to think you know what you're doing. Okay, stay right with me. I want you to hit import export tool library. Okay, lots of stuff going on here. We're going to export auto and manual tools, the very top one. Okay. Now, make sure over here you have your folder selected, your ThawSpace folder. And then over here, I want you to hit create directory. I want you to call this your PMTD 125 mil library. Okay, PMTD 125 mil library. Something wrong? Okay. Import export functions. Import export tool library. Export auto manual tools. Okay. Your folder selected. Create directory. Name it PMTD 125 mil library. We're going to have a lathe library too, so I want 2 different folders. Okay. We got that typed in. Hit OK. Now you notice over here it created a subfolder inside of our folder. Click on that subfolder, so that's where we're going to save this at. And then down here, I'm going to change the name. Leave the .tcm. It needs that extension. Okay, don't take that extension out. Make sure it's there. You're going to do your first initial last name. CNC mill library. First initial last name dash CNC mill library. And then it should have the .tcm at the end. Okay, and then hit export. Auto and manual tools were mapped successfully. Good. Okay. All right. If you did that right, if you go to your file folder down by the Windows Start button and open this up, and you go to your tool, your thaw space folder, you'll see in this folder now, we've got a mill PMTD 125 mill library folder, and inside of that there is our tool library. Okay, it also, if you noticed when I hit up, since we went and saved the file again, look at the time and the date stamp where it's updated the NC state. So those tools are saved with that NC state too. So I've got them, basically I got the tool library kind of in 2 different places. Okay, we're going to use the NC state files more than anything because it brings in a lot of other stuff that I want to not have to go in and manually set up. But if anything crazy happens, at least you got a backup over there with your tool library. Okay, all right, we're going to create the last 5 tools and then we're going to resave it again, okay? So let's go ahead and do that. Let's go to our tool setup, Control T, icon up here, or you can go over here to tool review and tool setup. I don't really have a preference on how you get there, as long as you can figure out how to get there. Okay. All right, tool 6. Tool 6, if I recall correctly, is the spot drill, correct? 3/8 spot drill. Okay. So we're going to tell it that it's a spot drill out of our list here. We're going to tell it that it's a .375. 5 inches in length. And then for the angle, okay, for the angle, we're going to type in 90 degrees. We're going to use this 90-degree spot drill. We're going to use this 90-degree spot drill several weeks from now to put a 45-degree chamfer around the tops of parts. We're going to chamfer edges, chamfer hole edges, and do things like that. Most of the drilling we do, or spot drilling we do, is going to be done with this. Towards the end, we're going to use that center drill a couple times, and only just because I want you to learn the center drill formula that I'm going to give you. Okay, you know, your center drill's got the point on it, which numbered center drills, that's a set length, and I've got a chart that I'll give you, and then there's a formula to calculate how deep do you need a center drill to leave the right size chamfer at the top of your hole in a mathematical way compared to what we do out there, which is right. Okay, we want to do it. We want to be able to program the machine to it'll get real close, and then you can look at it and be like, I need to go just a little deeper, or that's way too much. I need to back off a little bit. But at least it'll get us that starting point. Okay. Okay. So for the spot drill, we're going to look at our chart again, and we're coming down to the bottom down here. Okay, we're coming down to the bottom of the chart. Now, I will tell you this. Notice 90 degree equals 75% of similar size 118 degree drill. So we're going to run it at 75% of what we would do with this. What this is all 118 degree. Okay, so for a 90 degree spot drill, and we're setting up a high speed spot drill for aluminum. So our cut speed would be 250, but since it's 90 degrees, I'm going to take 250 times 0.75, 75%. So I'm going to use 187.5, 187.5 for my cut speed. That goes right here, 187.5. Oh, it doesn't want the point, so we'll just leave it at 187. Anytime, when it comes to cutting tools, anytime that you got a situation, if you round down, you're going to the safe side. So our drill diameter, or drill RPM is going to be 1905. Okay. We're going to use coolant. Okay. Our feed per rev for this drill. I'm going to give you a chart that kind of shows you how to calculate this, because if you look, and that's one of the things I want to give you as a formula on how to figure this out. On the chart, you just kind of got a range here. Like it basically says anything from 3/8 to 1 inch, 8 thou. Well, I don't really like that. That's a pretty big range for a lot of different diameter tools. Okay, so what we're going to do here is we're not going to jump the 2/10. We're going to go 6 thou here with this tool. Later, when I get that new chart to you, we'll probably come in and we'll make a official adjustment to it. Okay, so for right now, we're going to put 6 thou per rev. Notice when I say per rev, for end mills, it's RPM times the number of cutting edges times the feed per tooth or feed per cutting edge. For drills, it's literally an IPR, inch per revolution, times the RPM. Gives you your inch per minute. So you don't have, for drills, you don't have multiple cutting edges. Okay. Yeah, sometimes you might get like a 2-flute drill or something, but most of the time for your regular high-speed drills, everything's based off the center point, the drill point. So we do a 1 there. And as a matter of fact, if you notice, when we plug in 0.006 here, it doesn't, WinMax doesn't care what I plug into the flutes. It doesn't change what the feed rate does, because it's going off the drill point with a feed per rev. No longer is it a feed per minute, it's a feed per rev. Okay, where tool 5, our end mill, was a feed per flute. All because I selected the right tool type. WinMax makes that change. Okay, so we're going to feed this at 11. And there's our spot drill. Feeds and speeds are make or break situations. I get calls sometimes from employers who are like, hey, whatever you're doing with feeds and speeds, we really like it because student X came in here and they don't just go for it and guess at what they're doing. And then sometimes I get a call from an employer like, hey, do you even teach feeds and speeds? This guy came in here and all they do is program everything at 2,000 RPMs. Yeah, I spend time on it. I spend a lot of time on it. I go pretty deep with it. But sometimes you can always lead a horse to water, but you can't make him drink, right? So it's important that you understand how to calculate these, and it's all about these formulas, just plugging them in. Okay, let's do tool 7. Tool 7 is a 1/4 inch drill. Now for tool 7, since it's it's going to be a 118 degree drill, we can use our 250 cut speed. So we'll plug that in. So 3820. Remember, we're going for aluminum, not steel, what you're used to out there, because you're probably going, man, that's a lot faster when I run my 1/4 inch drill out there. Well, out there, you're using 70. Okay, that makes a difference because you're cutting into different types of steels. This semester, you're cutting into tool steel and stuff, certain parts. So, your RPMs are even lower, right? You're dividing that in half for tool steel. I imagine steel is at the kind of the go-to. divide your 70 in half, so you're doing 35. You know, because you don't want to tear it, you don't want to burn up all your drills. So 250 feet per rev. Let's look at our chart here. For a 1/4 inch, we're going to be down in this 4 thou range. We're going to just plug in 4 thou. So our feed rate's going to be 15. Everybody good on tool 7? All right, let's go tool 8. It's a number 7 drill, so 0.201. Now, let's say I don't know that's 201. I get a drill and they say, hey, you're setting up, here's the number drill I want you to use, and this one's a decimal. And then maybe my drill chart's not in front of me. All right, so my calculator, I know this is one of the ones on the quiz that asks for a drill size. Wants to know what it is. So my calculator, I can literally hit the drill size. So I can come up here and I can go convert. Oops, not convert. Unconvert. Drill size. And I can start walking through. Now if I know the letter, think about this for a second. There's a way to plug the letter in.
I just typed 7 in.
Type 7.
You can hit set. Okay, yeah. There's a way to do letters too.
Convert alpha.
Is that it?
Yeah. Convert 8 and then go to alphabet.
Ah, there it is. So yeah, you can get your letters and then you can hit for K, convert drill size. Maybe not.
No convert, just hit drill size.
Just hit drill size, sorry. Convert alpha. There we go. Then you hit drill size. There it is. Okay. That might be the one that's on the quiz too. Pretty sure it's a letter F drill. Okay. All right. So 7 drill size 201. Hopefully you know that what a number 7 drill is by this point. You've done a lot of 1/4 20s, I imagine. Are you all doing the die or the mold right now? Mold first. Okay. So you got a few 1/4 20s, but when you get to the die, you do a lot of it. Dowel pins, lots of dowels, lots of 1/4 20, holding all your parts and pieces where they go. We're going to plug in 250 for our cut speed. Our feed per rev. Okay. So this gives us a range of 4 thou for here. We're going to do 3 thou. So we're going to feed it 14. What your new chart is going to give you, and what we'll go back and we'll modify these and resave them. What the new chart's going to give you is I'm going to give you a formula that I found on Precision Twist website for high-speed drills that basically gives you, like, here's your starting chip load or feet per rev to your end feet per rev. You plug in your drill diameter, and it helps calculate where that falls into that range based on the diameter of the drill. So, everybody good there? All right, tool 9 is a tap. Cool thing about a tap, 1/4 20 tap, right? Cool thing is I could plug in the info I know. I know its major diameter is 1/4. I know it's TPI, but I can also click this little icon right here and tell it I'm doing an inch, and then I can sit here and say, okay, let's see, where's my 1/4 20? Am I blind? There it is, the first one. I can click on that and hit select thread, and it pulls the what I should know if I, but sometimes I get a thread I don't know. Okay, I know 1/4 20, but maybe I've got a metric M12 1.75 thread. It'll pull the metric conversion in for me. Watch this. This is what I love about WinMax 2. That was an M12 1.75, right? I think that's what I grabbed. Yeah. Okay. Let's say I want to convert that back to metric. Watch this. Down at the bottom, you see where it says inch on the screen? If you click on that, and it says, do you want to switch the units to metric? And you say yes, it converts everything to metric. Now, it doesn't just do that tool. It does everything. Everything's in metric now. So all my numbers here look a little different. But to convert it back, I just hit that again and tell it yes to switch back to imperial, and it converts back. So there's times where we get tooling, not necessarily the cutting tools, but like, for instance, on the lathe, our live tooling comes, and the gauge length of those is a metric, like 100 millimeter number. So I can convert 100 millimeters, or what I can do at the control when I'm plugging in that projection length of that live tooling drive, I can just hit the button down at the bottom of the screen, convert to millimeters, plug in 100, and convert it back, and it'll automatically do the math for me. Okay, it'll automatically convert that for me. So, quick and easy, dirty conversion options. Speed, okay. At the bottom of your chart, you see where it says tapping. RPM is 25% of the same diameter drill with a max of 400 for generic import taps. That's what that means. If you're buying a Hurdle or a Interstate, a cheap tap because it was the cheapest one, you only need to do a few holes, and you're not buying like a performance tap that's going to have feeds and speeds data given to you. We run it at 25% of the same size drill. So what I know is tool 7 was my drill, so my RPM was 3820, but when I type in 3820 times 0.25, that's 955 RPM. Nothing over 400. So for this tool, I would just plug in 400 there. It doesn't have a spot for the feed rate, but when we get to the point where we're doing some tapping, which won't be too long down the road, I'll explain that to you. Tapping, the feed per rev, okay, or the feed per, if you're doing feed per rev, which we're going to do everything in inch per minute, feed per rev would be exactly how much the pitch of the thread is, right? So 1 over 20, it needs to feed 50 thousandths per revolution. Okay, 50 thou. But we're doing feet per minute. So the way we calculate that is we take our RPM divided by our TPI, threads per inch, and that's how we get our feet per minute. That's right there under it, or right to the right of it. IPM equals RPM divided by TPI, or RPM times pitch. 400 times 0.05, which is the pitch, is 20. Quarter 20, 420 is kind of my go-to. 3/816. I run my RPM at 32 because oops, sorry. 320 divided by 16 is 20 inches a minute. I pick my RPMs as a number that will divide equally into my taps pitch. Does that make sense? Okay. Any of those generics, I'm usually, and even like the quarter 20s, a lot of times when I'm programming, and the way I have it in my library, I actually have this at 210 inches a minute. I'm not even taking any chances. I don't want to break a tap. Okay, so I'm going half the amount that I'm telling you that you can get away with here. But like I said, I just slow it down. You can always slow them down and things will work out. It's that one time that you push it a little too fast, things end badly, right? Okay. All right, last tool, tool 10. Okay. Tool 10 we're going to add in here. We're going to tell it that it is a center drill. And we got a lot of data at once there, right? A lot of data for that center drill. So, I can't remember where it's at in your books. I know it is in your books, but what I also know is it's in this. Okay? It's in this little guy. And that's what I want you to look at. If you've got this with you, pull it out. Go to page 23. Page 23. Is there a center drill chart in your calculator book too? Isaac? Oh, no, this is the book we're. This book. This guy. The little Herco book. So there's a center drill chart. Center drills are standards. They're standard size center drills when you order one. Like you have, I think you've got a number 4 or a number 2 that you get with your toolkit. And then I believe you get a number 6, half-inch one, right? No? Yeah? Maybe? Not sure which 2 you get? I'm not for sure either. I could look at the tool list and tell you, but you get 2 center drills when you get your tool set, and they're 2 standard sizes. So on this chart here, what size does it say we want? Number 4 center drill. No problem. Body diameter of a number 4, as I look at this chart, is 5/16. Length, I'm going to tell it 5 inches. The tip angle for a center drill is 60 degrees. And then the tip diameter for this center drill is an 1/8 inch. That's it. I just pull it off that chart, plug in my information there. We're going to learn how to plug in it. It's drawing, it's looking at it and creating the profile of that center drill based on what we just told it. Okay. RPM for the center drill. Okay, same thing. I'm going to do 75% of the same size drill or the similar. So we're going to use basically that same cut speed we used over here, 187. It's saying we can center drill at 2286 RPM. Remember, we're in aluminum. Don't go out there and crank the mill up to 2200 RPM. Okay, you're still doing 1,000, I imagine. All right, 1,000. Feet per rev for this, we're going to calculate our feet per rev based off the tip, not the body. We don't want to break the tip off for a center drill. So since the tip's an 1/8 inch, we're going to do about 2.5 thou for right now. So we're going to center drill at 5 inches a minute. Okay. All right. We've got our 10 tools. If you click on the little next to the tool setup button, this tool review button right here, and then uncheck show only used tools, you should see all 10 of your tools right here. Okay. Everybody got them all? Looks good? Okay. I'm going to go back over to my program manager and I'm going to hit save again. That just saved these tools to my NC state with my notes file. Okay, my NC file just updated again at 11:19 a.m. There it is, right there. I'm also we're going to go to the input button. We're going to go to import export functions. And we're going to import export tool library, import export tool library. Export auto and manual tools. Click on that. Just click on the one there in your folder that's already there and hit export. When it asks if you want to override it, you're going to say yes. And And it's going to give you the auto and manual tools mapped successfully. Now we've updated our tool library file. 11:20 a.m. it was updated. Okay.
So did that not save whenever we just hit save before that?
Not to that file. It saved it to the NC state.
Just to the other one?
Just to the NC state. So you basically have, if you lose this, you still got this. What will happen is you're going to start coming in and you're going to load the NC state in from one file, but then when we start creating like new files, you're going to save it and it's going to save a new NC state. So the files are going to keep, the tool library is going to keep loading in with the program when we load that NC state. This is basically just a backup. Just in case something happens to all our other files, we want to keep this. All right. Did I go through how to back your thaw space up the other day? Okay. So at the end of the day, what I would like you to get used to doing is plugging your thumb drive into your computer. If you've got it with you, great. If you don't, that's fine. Try to make sure you start bringing one. Okay? Plug your thumb drive into your computer at the end of the day. Some days you might do homework outside of here, and you've got to bring what you did outside of here and put it onto your thaw space. But at the end of each day, what I would recommend you do is go to your thaw space folder, go to the thaw space T drive, find your folder, which for me this is section 1. I'm going to right click it, I'm going to send to, and I'm going to pick my thumb drive out of the list. And now there's my file I just put there with all my updated files in it. We're going to do that again on Monday. And when we do that, it's going to say, hey, you want to overwrite these files? I'm going to say, yeah. Go ahead, just add what I've done today to what I'm doing. All right? I'm going to work with you really diligently to keep these files managed. I keep talking about that, but I've got students still almost graduating here in a few months. When I go and they open up their thaw space folder, it's like, whoa, hey, let's try to keep this organized. Let's learn how to be organized, because it does improve efficiency in the workplace, and it will make you have lots less headaches. When I say open this up and you got to go find it, you're going to know exactly how to get to it. Okay? Questions? Yep.
Say you do have like quite a few files and you're working on like a particular project. Is there a way you can pin one like to the top of the file list?
What's that? Move it to the top of the file list? Yeah, you just, if you want the one you're working on that active, you just hit date modify and it'll, yeah, whatever your last one is, you just sort it by the date and it'll give you the newest one. All right, last thing. Before you leave, we got to look at some G&M codes. So I'd like you to jump over to your part programming right here, which is where we got those notes. Okay. And let me see which ones we're getting here. We're getting a list of about 1, 2, 3, 4, 5, 6, 7, 8 new ones today. 8 new ones to be learning. The first one is G0. Rapid interpolation. Just means that it's going to go from A to B in a straight line as fast as that machine can. All machines have a max rapid. These machines out here, it's like 1,400 inches a minute. We've got them all backed off to considerably slower so that big bad things don't happen. But in industry, usually you're not putting the brakes on them. You want to move as quick as possible when you're running parts. G1, linear interpolation. Okay. Straight line moves. Straight line moves. Anytime you're, this will be, I'm putting our comma here. It's done with a feed rate call, so there's going to be an F command in those lines. As we start programming, you're going to see that, how we do that. It's going to have an F with the number of whatever the inches per minute that we want it to feed at for that linear feed rate is. Okay. G2, clockwise, circular interpolation. Clockwise turns. Left, or no, be right turns. All right. Clockwise. So right turns. Anytime we got to make a right turn. So G3, counterclockwise, circular. And then we're going to have our first little batch of M codes, miscellaneous machine function codes. So the first ones I like you to learn is M0, program stop. If we hit an M0 in a program, everything shuts off, machine stops. What do you want me to do next? Usually there's going to be a comment there that says measure this, check this, make sure your drill didn't break so you don't break your tap, you know, things like that. When we put it in there, machine program stops are when we want it to stop every time at that point in the program. We want it to stop right here so I could do something. M1, optional, if I can spell optional, stop. This can be turned on and off at the control. So when we're running a program, when the program's running, there is an optional stop soft key on the screen. You can turn it on, and that means every time it hits an M1, it's going to do the same thing it does at an M0. But let's say we go through and we get all our adjustments made and the program's running good and we're making good parts, so I don't need to do that every time. So then I can shut optional stop off, and what it will do then is when it sees an M1, just keep on trucking. It won't stop. It's optional. We get to choose if we want it to do it or not. M2, program end. Program end is something pretty common in like the wire area. The program will stop at the end, and because you got to come in and manually like jog the head up and make sure your slug's out of the way and all the stuff's good. Or you know, sometimes on the M30 you want it to stop there and just stop. But typically on the mill we use an M30, program end and reset, which means that hits the end of the program, goes back to the top, and it's sitting there ready for you to change the part, load another part, and hit go. So on an M2, you've got to load the part, unload, and then you also have to reset the program manually. On an M30, it's going to automatically reset itself and then wait for you to tell it to go again after you've got everything set back up and ready to go. All right. Does everybody have those 8 codes typed out? You can hit save. I'm also, since we just did that, I'm going to go here to my thaw space folder, and I'm going to right click and send that to my T drive, or to my thumb drive again, because I just updated it on the thaw space. This is what I was talking about. When this comes up, I'm just going to hit replace the files in the destination. Okay, send my new stuff there and just update them. Okay. Now, you want to study these notes at home, but you don't have WinMax yet. All right, which is fine. You don't even have to get WinMax, but you want to look at these notes. All right. Well, when you get home and you want to see these notes, all you got to do is this. On the NC file, the FNC file, right click, open with, Notepad. Tell it OK. It'll open up in Notepad and you can read it just the same. Okay? Or any Word, Microsoft Word, you can open it in Microsoft Word. You can open it, it's going to open up as a text document anywhere you want to open it. Okay? I think, I haven't done it, but I think you could even drag it into like the cloud, into Google Drive, and open it with like Google Docs. So, questions? All right. That's what I got for today. Now that you've got these new G&M codes, be learning them, be studying them, be studying all of them, but really hunker down on these ones here. We're doing pretty good. You know, everybody's scoring over 50% on these right now, but as the list gets bigger, we got to keep doing them. So flashcards, practice quizzes. If you want to get on that Circle In and create something on there, you can earn yourself some of those bonus points to get you a few cents off of something or whatever. I don't know what it is. They sent out a thing about gift cards. You can get on there, and if you use it, you can get gift cards. But somebody said they got on there and looked at it, and it takes like a lot of doing, a lot of practicing to even get close to anything worthwhile. But it's not really about the gift cards. It's about making sure you know these G&M codes. Okay? All right. That's all I've got for today. You're free to go.